Professor at a school close to here, the New Jersey Institute of Technology. And I want to talk to you about a solution that we've developed, an open source framework that we call Arachne, that really helps us solving some massive scale data and graph analytic problems. I'm going to focus on the graph analytic problems. So I'll tell you first a little bit about myself, the motivation behind the problems, and then the solution that we've been developing that has now quite a number of customers that are using it. The problem that we faced was that we often are dealing with graphs that are enormous in size. Think of the biggest graphs that you've ever seen or used, and the ones that we're often dealing with are orders of magnitude larger. And so we don't have, in the customers that I work with, we don't have any enterprise class solutions. Often I'm working with analysts that use a tool like Neo4j or something like that. And then they get to a point where what they want to run is just too large to fit into a Neo4j instance, or the time to get their solution takes too long. And they may often have terabytes, in fact, tens of terabytes of data, and want to run graph analytics on, and they're just completely stymied with how to solve those problems. So that's where Arachne comes in, and it's something that we've been building over a number of years that has helped analysts solve some of the largest graph analytic queries. And recently, we've expanded Arachne to include property graphs, which is just really another word for knowledge graphs. So we're able to work on knowledge graphs of just humongous sizes. And then the other challenge that we had was maybe 5, 10, 15 years ago, we were dealing with analysts who could program in C and MPI and all of these high performance computing languages and use supercomputers to get this done. Today, not so much. All of the analysts that we deal with, that we try to support, they speak the language de franca of data science, which is Python. All they know is Python, which is great. That's really productive. But then I say, I want you to use this really specialized supercomputer to get this work done, and they have no idea what I'm talking about. And so what Arachne purposefully did was figure out how to make this high-performance supercomputing accessible to anyone with Python running in their Jupyter notebook or wherever you happen to run Python. How are you able to work on problems of tens of terabytes in size for these massive knowledge graphs, but to be able to do it as simply as you could with running something that fit very easily on your laptop. So that's what I'll be talking about today. I'm a professor at the New Jersey Institute of Technology. 5 years ago, I moved to NJIT in order to direct an Institute for Data Science. And also I founded a Department of Data Science. Previously, I was at Georgia Tech for 14 years, where I founded and then chaired the School of Computational Science and Engineering. And I have a long history of working in graph analytics. In fact, I've been in the space of parallelizing graph analytics for over 40 years. So it's a place where I've had a lot of experience. If you don't know about NJIT, for instance, I'll just pull out one headline from the news last year. The Wall Street Journal, in their College Pulse rankings, named us or ranked us the #2 public university in the US. If you look at both public and private, they ranked us number 19 in terms of the excellent students that we have. And I direct an Institute for Data Science, which is made up of a number of centers. And I tend to apply graph analytics or work on solutions for real world challenges coming from areas like urban sustainability, healthcare analytics, looking at trustworthy, free and fair elections, insider threat detection in large organizations, utility infrastructure problems, cyber attack defense and attribution, monitoring disease outbreaks, and so on. And this work is done across a variety of centers. So often when I'm thinking about data and graphs, the way I get to graphs is maybe a little bit of a, I think about the problems that I have kind of in this data quad. So initially I have a lot of data. And if I think about my data with objects with on the x-axis with known objects on the left, to unknown objects on the right, and then patterns within that data from known patterns on the bottom to unknown patterns at top. This breaks apart the space of this data quadrant to these 4 quadrants. On the lower left, where I have known objects and known patterns, well, I don't really need a graph here. I know that my relational databases can take schemas with tables and relations between them and solve very traditional database queries in that regime. Or in the upper left-hand quadrant, where I have known objects but unknown patterns, while I see a graph here, I don't necessarily need graph technology. For instance, vertical databases have helped solve problems in this domain. For instance, I may be a CISO, a Chief Information Security Officer at a company looking for insider threats, and I have one employee who's tripped some tripwires, touched some files they shouldn't have, accessed some web pages they shouldn't have gone to, and I want to find out, are they doing something with malfeasance? Are they in collusion with other employees? Or was it just human nature and some accidents that happened? So we could look at these as graphs, but we don't need graphs to solve problems in this space. On the lower right-hand quadrant, I have known patterns and unknown objects. Again, there's some graphiness to here because maybe I'm looking at some observed activity, and then here there's some inset pattern of, in this pattern, there's 2 people living together. They're observing some building. One is renting a truck, one is buying fertilizer. Maybe that's a pattern that isn't so great, and I'm in security and I want to try to find that pattern in the real data. So we could use graph analytics, but also some traditional technologies for databases will work in that regime. But where I tend to work is this 4th quadrant of unknown unknowns. And here's where I work with analysts who are given massive quantities of data, typically unstructured data, and they're trying to understand, are there any surprises in that data? And what I want to be able to do is move those surprises out of this 4th quadrant and use graph analytics and knowledge graphs to be able to reduce that surprise. And this is really the motivation that got us working on Arachne that I'll tell you more about soon. So for instance, you may think about, well, what are big surprises? For instance, the COVID-19 pandemic, knowing that there was SARS-CoV-2 that was coming around that was going to really impact the entire world. Or maybe there's a new piece of malware that is exploiting some zero-day exploit that's going to be very dangerous and impact all businesses and governments around the world. Those are the big surprises that we may be looking for. So I think of this as graph data science, and this is the space that we really address. We're not just doing graph alone, we may be doing data science and then extracting out of our tables and our data frames graphs, and then we're running graph analytics on those knowledge graphs that we build. And there's many different problems that fall into this space, everything from healthcare to understanding massive social networks, business intelligence, systems biology. We even work on places where we're trying to model and simulate full economic, social, political models of entire nations to understand how they'll react to policies or new treaties and so on. So all of these really require predicting or influencing some change in real time and at this massive scale. So that's really the heart of what we're doing. So our first motivation, as I mentioned, comes from trying to solve real world grand challenge problems. So we're solving real world problems in business and government and other places, and they tend to be very large. If they weren't large, there's a lot of technologies here at this Knowledge Graph conference that you could buy and use that would help with your problems. But when you get to places where it just doesn't work, because you have just an enormous scale, that's where we've been trying to build some tools. So our second motivation is that many of the problems that we're looking at, and I'm preaching to the choir here, at KGC, we require graph analytics to solve. So these are just a couple cartoons of problems coming from COVID-19. This is visualization of a high voltage transmission system, defined edges with maximum flow. This third image is finding the communities among authors in areas of corporate social responsibility, inside to metrics and other places. So everywhere we look around, we see a lot of graph analytics that we want to apply to our problems. And then third, I mentioned this earlier, what I have here is the last, say, 10 years of looking at GitHub pulls and push requests, seeing what languages are being used. In the old days, we saw traditional languages, C, C++, Java, maybe some JavaScript. And now what we've seen in the last few years is that Python has overtaken everything. There's no other way to interface with today's data scientists without having Python interfaces. And so we took these three motivations and really wanted to put them together. I actually think if we look out a little bit, Python will probably go by the wayside. And I think the next big language that we're going to see here is English. We're going to be using GPT to communicate all of our programming and computing needs. And Python, enjoy it now because its time is numbered. So these motivations, these three motivations overlap. Our need to have to generate insights from massive graphs and to do it in near real time. We want to use Python, and then we want to use graph analytics. So it's the scale, the graphs, and doing it with Python in the front end. So that's really this, what we're doing here is pulling all of this together for the first time with an open source solution. So I think I've mentioned much of what's on here. What I'm going to talk about today is all open source. Every part of the components that we have are open source. And in fact, at the end, I'll pull up, or you could look at GitHub. If you go to the Bears R Us repository and search for Arachne and Arachne, you'll see these projects that I'm talking about. And there's tutorials, there's papers, there's training, there's Docker images. There's a lot there. And the code that we've been developing, we do have real world customers that are using it in mission every single day. And so we continue to build out these frameworks that I'm going to tell you about. Now, why are we doing this? Well, there's existing tools. We all know in Python, there's NetworkX. Everyone here has heard of it. There's NumPy and Pandas, which manage data frames and doing some array operations in NumPy and so on. So NetworkX is mostly Python with some minor parts in C++. NumPy is a Python wrapper to C++. Pandas uses NumPy. And then Arachne is a framework that we also developed as our base layer that is really running data frames at scale, but it doesn't have a graph component to it. So as I look at these and I'm trying to handle massive problems in near real time, NetworkX is mostly running sequentially with a single thread. This isn't scalable. It doesn't let me address larger problems. And so while it's great for prototyping and small problems, it's not really helping me as I'm trying to work on these bigger problems. NumPy works really well. However, it doesn't work on distributed data where I have my data maybe spread across multiple machines. Pandas, likewise. And then Arachne that I mentioned, I'll tell you a little bit more about today, doesn't have any native graph-centric operations, which is what Arachne is providing on top of Arachne. So we acknowledge the National Science Foundation that has been funding us to build out this framework, and we've been at this now for a couple of years. So this project and the tools I'm going to mention are really about 3-4 years in the making. So now I'll get into the depth of Arachne after giving you the motivation, problems that we're trying to solve, and here is what Arachne is. It's an interactive property graph analytics framework at scale. So by interactive, again, we want to have our data scientists interfacing with Python in a very familiar type of framework And instead of using NumPy and pandas, they're calling Arcuda, the Greek word for bear, and instead of Network X, they'll be calling Arachne. And so it's not a one-for-one replacement, but the APIs are fairly similar. And we're getting both productivity and performance using a number of tools. So first, we have Python at the front end. This gives productivity and makes it accessible. What we're trying to do is democratize the ability for anyone around this planet who has access to a computer and Python to be able to run large-scale graph analytics. And then for performance, we're using a productivity language called Chapel. Has anyone in here heard of Chapel? So I'll give you a short crash course on Chapel. It turns out the US government in a DARPA program about almost 25 years ago, the High Productivity Computing Systems program started funding a supercomputing company called Cray to develop this language called Chapel. And Cray recently was acquired by HPE. So now this is HPE's Chapel programming language. And the language was really trying to make high performance computing or parallel and supercomputing easy for the masses so that you don't really need to know extensive training to be able to program it. If you could program, say, C++ or Java, then Chapel should let you be able to program efficiently and easily high-performance computers. The Chapel programming language, even though it's from HPE, is actually open source. You can get it on GitHub. It's freely available open source. So all of the tooling that I'm going to tell you about today is open source. And also a couple of years ago, HPE started really heavily investing to make Chapel more robust, to make sure that the releases are non-breaking changes, that there's a roadmap, so companies could start relying on Chapel. One of my friends, Michelle Stroud, is now the project manager at HPE for Chapel, and it's really come a long, long way. Also, Chapel, I'll tell you a little bit about in the future, but you can run it on a laptop, you can run it on a cluster, you can run it on a supercomputer, you can run it on a system with GPUs. And without any changes to your source code whatsoever, you can typically get efficient code across any parallel platforms. And so I have students developing the work that I'll tell you about here. Many of them have no idea anything about parallel computing. And on day one, on their laptops, they're developing in Chapel, writing code. And that same code we're running on some very large InfiniBand clusters and getting just incredible performance. We're getting speed ups, we're getting quite performant code. And so that's the productivity gain that we have. So here's a picture of how this is working. We have a user on the lower left, and they're interacting with their Jupyter notebook. I know it's an eye chart and you probably can't read all the text in here, but this is the same as you'd run with NumPy, Pandas, Network X. So they're loading in Arcuda and Arachne up here. They're loading in a graph, and their graphs that they load in could come from CSV, HDF5, Parquet files, and so on. So pretty much any standard to be able to store data can be ingested. A graph gets built, and it's a property graph. So we have a feature where you can extract particular labels of the types of vertices or edges that you're interested in. And then on the resulting graphs, you can run and construct the graphs and then run a graph analytic like connected components, triangle counting, or some other graph analytics. And I'll tell you more about the graph analytics that we currently have today. Now, what's really happening is that user has attached over a ZMQ, a zero message queue, to a backend server. And that backend server is the Chapel server. I just told you a little bit about Chapel a few minutes ago. And that's where all of the big data is loaded. And their operations are really sending messages back and forth to the server under the hood. They don't see that. It looks like their Jupyter notebook is just responsive to them. And on this Chapel server, you have your arrays in distributed arrays, metadata, And this server could be running, as I mentioned, on your laptop. It could be running on an SMP. It could be running on a cluster. It could be running on a big supercomputer with InfiniBand. It could have GPUs across the system or not. But this is a very portable type of server where it runs. There's a number of modules that Arcuda provides. This is the base of Arcuda. And then what we've been building out on top of Arcuda are these yellow or gold modules. That's Arachne, the graph analytics. So Arachne is really just Arcuda modules for graphs. And I'll tell you a lot more about this. So as an example, we may start from data in some spreadsheets and some tables. And this could be terabyte size, so tens of terabytes, if you will, or it could be 100K, it doesn't matter. It will work small or large. And we have some functions to load those in. We can build a graph data structure from it, and then run our graph analytics on that data structure, the same you would with, say, Network X. So I'll give you a crash course on Chapel. So this, I know you're not all programmers or developers, but I'll show you a little bit under the hood of what Chapel is doing. And we're using this really to make the parallel computing part of this really, really easy. So this is what we do as developers. And if anyone in the room wants to contribute to use Arcuda and Arachne and contribute to it, then by all means, feel free to do so. We already have a number of developers and contributors on GitHub, and we welcome people downloading the code, trying it out, kicking the tires, developing and using that. In fact, when we develop for Arachne, about 80 to 90% of the work that we're doing is really writing routines in Chapel, and then we're stubbing out some front ends to an API that are callable from Python. So for instance, in Chapel, a couple of definitions. We have our distribution of the data, which is how an array's index or domain set is distributed onto different computing locales. Well, what's a locale? A locale is really a computational unit. You could think of it as some CPUs and memory. Usually you could think of that as like one node in a compute cluster, but it doesn't have to be physically mapped out that way. Multi-locale just means that a program has access to more than one locale. For instance, there's distributed memory. You may have a cluster of 1,000 nodes that you're putting your data on, and that multi-locale represents the entire machine. There's fine-grained communication, meaning a memory access from a locale can just be performed one after another, or coarse-grained communication where a bulk of data is sent or put between different locales, and that's usually done through something called aggregation. Aggregation is a way to bulk it up and make it more efficient. We also, question? Yeah, so a Chapel server can be anywhere you want it to be, as long as it's accessible through an IP address and a port. So for instance, we work with analysts that may run multiple Chapel servers, and they may put, say, different graphs on different Chapel servers for better performance. There's a feature coming. I don't know if it's out in release yet, but in development, we're allowing a Chapel server which have multiple users being able to attach to the same Chapel server and treat the graph kind of like read-only, so that they can all share that graph as well.
Is there any concern with is there header concern with GPU nodes?
That's a great question. Whether or not we can, so there's Chapel has multiple ways it can be compiled. There's Chapel for shared memory and Chapel for distributed memory. So if you know, for instance, you're running on just one big server like an SMP with multiple sockets of processors, and each one of them has tons of cores on them, then you compile Chapel in shared memory mode to get a higher performance than running on a distributed memory server. In terms of heterogeneity, most of the systems that we run on, that's a good question for the HPE team. Most of the machines we run on are like an InfiniBand cluster where the nodes are generally very similar to each other. They don't have to be exactly the same, But I don't know if you can use GPUs just on one node and not on another node versus GPUs across all of them. That would be a good question. Any other questions? Okay. So I mentioned I did that slide. So there's different types of parallelism, and this is really all our developers or programmers need to know. There's task parallelism. So this is something like a co-for-all loop, which creates one task per iteration of the loop. So often in a loop, if you use co-for-alls, there's a lot of tasks created. Imagine I'm looping over a billion items, I have a billion tasks created. There's also data parallelism, which is called a for-all loop. And in a for-all loop, I can create tasks dynamically, depending on the size of the data, and really bulk up some of the loop iterations. And I should mention, I think these slides are available on the, either on the website or in the app. But if not, I'm perfectly happy to share all these slides. Yeah, I think I saw them there already, but I could be wrong. And I've only, on the slides I'm presenting right now, I only fixed a typo or two. So the ones that are online should be pretty close. So for instance, the difference between task and data parallelism, if I have an array A with 64 elements in it, and maybe I have 4 available threads, if I were to do a co-for-all, that means I'm going to create 64 tasks, and each one of them has just one piece of work to do. And if I only have 4 threads, 4 of those tasks can run concurrently at a time. So that's one way of thinking about it. But if I did the for-all, instead of having 64 tasks created, there's a lot of overhead to create a task. Here I just have 4 tasks created, 1 for each parallel thread, and they do each 1/4 of the work. So they'd be doing 64 divided by 4 is 16 elements each for this very simple piece of work. So when you're writing some code, you just have to be careful, what type of parallelism do I have? And usually you want to minimize the number of tasks, but not always. It depends on the actual situation. We also have in Chapel things called gets and puts. So you could imagine that you have a number of locales, and you could think of a locale as a compute unit, and there may be times where you're putting information from one locale to some memory elsewhere in the system, or maybe you're fetching or getting. These are seen as blocking operations. They don't complete until the operation has completed successfully. So what Chapel really gives us is a way to work through both the interface barrier and the resource barrier. The interface barrier is really the barrier to programming high-performance computers. Often to program high-performance computers, in the past I'd have to train students maybe a year, 2 years to be able to use C, MPI, OpenMP, CUDA, all these languages that really take heroic programming for just one of them, and then you want to put it all together. I want to program a big cluster. Every node has multiple cores and CPUs. There's some GPU acceleration. Normally to write code to do that is really challenging. Chapel makes that much simpler. And then the resource barrier is really the ability to connect what you're doing to a supercomputer quite easily. And Chapel is allowing us to really break through that barrier. So for instance, as I mentioned, you could be running on a shared memory machine, so a big compute system that's got multiple sockets, and every socket has a highly threaded multi-core chip in it, or you could be trying to program a distributed memory machine. And with Chapel, I can target any of these without changing any of the source code.
I saw the RAM, so data will be in RAM, it's not on disk.
Correct. So I'll go back a couple slides. In order for this to work, and one reason why we're doing this fast is that we do have our data in memory. That's correct. So we're addressing problems that have tens of terabytes. You may have problems that aren't that big, but you still want to use such a system. But as long as it fits in aggregated across the memory, you're fine. I don't copy the graph, for instance, onto every compute node. That graph is spread out across the entire system. So if I have nodes with 1 terabyte on them, and I have a problem that is a 20 terabyte graph, then I need at least 20 compute nodes. And chances are, if I have problems that big, I can probably afford to buy 20 compute nodes. I'm not selling systems here, promise. Question?
I mean, do you guys play with LNDB or RockCB type in process fast storage? Like SSDs integrated between
Using SSDs, so the problem with using anything that is more of a storage technology is often when we're looking at graphs, the performance bottleneck is that you're accessing an edge to get to a vertex, and from that vertex, you're looking at its properties and going to its neighbors. And you have very small communication that eventually are just spread out all across the machine. And your message size is usually very small, and to get performance out of any sort of traditional storage, like an SSD, you need to be able to do bulk reads and writes, not just these single ones. So I may be trying to get a page off of the SSD, and I only want about 4 bytes off of there, and my performance is going to be killed. So often we look at doing this in memory versus storage, but there are trade-offs. I mean, it is possible to do this with online storage, but there are trade-offs in terms of performance, speed, bandwidth, et cetera.
Is there a way to outwardly store it, or is it too unpredictable because of the shape of graphs and this?
In many graph analytic problems, the memory trace is not known a priori. It depends on the topology of the graph, the shape of the graph, the types of queries that are asked, the types of algorithms that are asked. And that is very challenging to know beforehand. And if you knew that beforehand, chances are you won't be running your graph analytic. And so it's very hard to restore the graph in a more locality-friendly way. And a lot of researchers have looked at this problem for the last 20 years. And it really is just a challenge, because if I optimize locality for you, then the next person running on that graph may have wanted it organized completely differently.
But if you do the distributed, don't we have to have some type of locality, or that's?
If you had locality, it would be great. In fact, my students, I have some PhD students working on that problem right now, but it's very well known in these types of graph problems that extracting locality is extremely hard. And again, I could have a graph, and for one analytic, maybe I want to run breadth first search through the graph. There may be one way to store it, and then if I think about running, let's say, triangle centrality, another analytic, I would have wanted to store the graph in a different way to get that locality. So even if I have a graph, it isn't clear what that locality means, because different algorithms will touch the graph in different ways. And these graphs often, when we're looking at graphs from some domains, like a road network is a graph. And if I have a road network, it often comes from a Euclidean geometry. Those are very easy to partition up and put pieces of it on different processors and run efficiently, because I only have to worry about communications on the boundaries. Maybe I have problems that work very well in these tiles of the graph. But if my graphs come from social networks, we're even working on property graphs coming from neuroscience in the brain. It's very hard to partition those graphs to give a very small cut of edges and then take pieces of that graph and put them in each one of these nodes. So for now, a lot of the work that we're doing, we just punt on that. We put the graph straight into memory wherever it is, and we realize that most of the accesses are going to go across a network. Other questions? So for instance, if these are my arrays A and B, and I want to do an operation, C down here. So my input is some scalar A times C plus B and stored into A. If I'm doing it element-wise, then on a multiprocessor, I would divide up the input into these contiguous regions and have one parallel processor or locale working in each of these regions. and no communication would be needed. Here, they're all working on local data, and I would have 4 tasks running if this was running on 4 locales, and all of the work would then be on each one of these locales. The gets, the puts, and the multiplication and addition would all be local to each locale. Unfortunately, this isn't what graphs look like. So this is great for dense numerical linear algebra problems, but graphs look more like sparse computations and not these very easy to partition problems. So if I take, let's see, what problem is this? Here's some code to do this problem that I just had on the last slide. And this is code that's using MPI and OpenMP in order to run on a cluster of nodes with multiple cores on each node. And this is about 60 lines of code. So traditional high performance computing, this is the code that would run that problem that I gave on the last slide. Such an easy problem, but yet this is the code that would be needed. And it's fairly good code, but there's a lot of pragmas, there's MPI calls, there's OpenMP calls, like a lot of things in here in order to get efficiency. But look at it in Chapel, here's the Chapel code. And this is why we like Chapel and we're using Chapel. Now it's what, 10 lines of code, not even, and it looks very natural. And this is the code that's running on any target that I mentioned, a cluster with multiple cores. And this is why we're using Chapel. So maybe you want to pick up Chapel for other problems that you might have, because I just absolutely enjoy programming in it. I won't go through too much more. There's ways to have parallel programs that aren't local. This is a distributed program, but it's running serial. And then this is a distributed and parallel program. So kind of the simplest code here is making use of all the resources that I have. So again, there's no communication. Now I told you about Chapel, that's the system that's implementing what we're doing. Now I'll tell you about Arachne and the types of algorithms that we have in our graph analytic framework. So the way we think about it is that we have some data that we're ingesting. And the data, as I mentioned, is often coming from big data frames, from tables, from big blocks. And we are able to read it in and then go from those data frames to build DI is our double index graph data structure. And we also have some graphs that we can generate just for testing.
Ingestion, is it parallelized and distributed?
Yes. So ingestion is parallelized and distributed. We're using a lot of tools to be able to load in whatever file format, ATF5, CSV, Parquet. If you have some other format, there's a very easy way to add that in. And we're using, in our systems, we either have in our CUDA implementation of ingestion, or we have other, you can write your own if you have another file format, or copy some of the tools to be able to do that. But all of this is done in parallel.
One quick question about Chapel is the language all imperative, or is anything like lazily evaluated or execution determined by compiler?
That's probably a great question for the Chapel team. So I mean, Chapel to us is a little bit of a black box. So it's open source, and it's really like an extension to C++. Imagine you're programming in C++, but you're given a data structure like a distributed array, and you just use it. And then you change the loop to a for all, and that's it. I mean, for our interface to it, it's very simple. But Chapel's doing a lot of things under the hood. I can't speak to all of it. I'd refer you to our friends at HPE for more details about Chapel. It's also open source, so you can look through and see what it's doing. So we often find in Chapel there's multiple ways to implement things, and we'll try things out. We'll iterate with the HPE team, and there's a great team there if you have performance questions or why does this work better than that. They have a couple of developers who've been working on this for 20 plus years who have a lot more insights. So we use it mostly as a black box. And then we can call a number of graph algorithms on the property graph that we built. So our graph data structure is not unlike CSV, compressed sparse row for holding graphs. I'm just showing you what's under the hood. We take our arrays of vertices or arrays of edges, and we basically just chunk this up and put equal sized pieces on each locale. Now, this is different from CSV because this data structure allows us to go from a vertex and find its edges in constant time, or if you give it an edge, you can find its endpoint vertices in constant time, which is something that CSV can't do. So it's CSV-like, but for instance, this little graph over here, 3 vertices, a number of edges. This is a directed graph. We could very easily create this data structure, and that's what's sitting there under the hood inside of Arachne. But this is the graph data structure for properties. What we do is we extend that data structure, and so every vertex can have 1 or more properties. I just show some examples with ints, unsigned ints, real numbers, etc. Could also be text, characters, what have you, and the same with edges. Edges can also have types associated with them. So we can have a vector of properties associated with every vertex or every edge, and our algorithms are able to use those properties to either select or operate on these properties in many of the algorithms that I'll tell you about. So we've just extended this data structure and are able to build property graphs in this way. In fact, some of our algorithms can write new properties. For instance, running a search and you want to mark a vertex as visited, you just create a new property for that vertex, like a Boolean, whether or not you visited it. Now, today we've implemented a number of algorithms, and this is just a subset of what we have. For instance, breadth first search is where you start at one vertex and you want to explore all the other vertices in your knowledge graph. Connected components to find the maximally connected set of vertices in your graph. Triangle counting. How many of you are familiar with triangle counting? So a triangle in a graph is very simply 3 vertices that have the 3 edges connecting them. And I don't think anyone, a data scientist, wakes up and says, I want to count triangles in a graph. Well, maybe I do, but usually most people don't think about that. But it turns out that triangles are very useful because if you look at parts of the graph that have more triangles than other parts of the graph that have fewer triangles, that represents some more cohesion or connectedness in that portion of the graph. So many operations that you may want in a graph, such as finding a community, however that applies to your application domain, the optimizations are often NP hard, meaning intractable, to do maximum modularity or minimum conductance. But there are triangle approaches where finding triangles you can do quite efficiently and quite fast. So often triangles are the basis of other analytics. You first find triangles and use that triangle in somehow to run other analytics. For instance, truss analytics are a surrogate for community detection. Trusses, and I'll show an example later in this talk, trusses are basically finding edges that have multiple triangles sharing an edge within that truss. And the amount of triangles supporting that edge gives me a truss, for instance, a 3 truss, a 4 truss, or a 5 truss. I'll tell you a little bit more about that in the upcoming slides. Or a new analytic from one of my colleagues, Paul Burkhardt at the National Security Agency, came up with a new measure of centrality called triangle centrality that we were able to implement in about 2 hours on Chapel from this brand new paper, quite an exciting centrality. How many of you have heard of between us centrality? So between us centrality looks at shortest paths in a graph and finds the vertices or edges, if you will, that are at the intersection of the highest percentage of shortest paths in the graph. So in some way, removing them breaks apart the graph, disrupts the graph, they're kind of congestion points and so on. Triangle centrality is another type of centrality that looks at the triangle support for vertices in the graph. And it's really, really good at finding some highly influential vertices in the graph that are completely missed by between centrality, closeness centrality, degree centrality, and all the other centralities, but are quite important. So we've started to like that. And we just finished some work on subgraph isomorphism, also known as pattern matching. So imagine you have a big graph and you have a little template of a pattern that you're looking for, maybe exactly or something close to it in your property graph. And subgraph isomorphism is the algorithm or algorithms that can solve that. In fact, we built this out recently because we started to apply our knowledge graphs to neuroscientists. We're working with some of the best neuroscientists at Harvard University that for the first time this last year have imaged an entire brain of a Drosophila or fruit fly. And for every neuron, they know the type of the neuron, they know exactly where their synapses connect to other neurons, and that's a big graph. And they had no tools that could operate on their petascale data sets for just 1 millimeter cube brain of a fruit fly. And so we have tacked on our Arachne subgraph isomorphism into their motif finding tools and are working on that right now to assist neuroscientists with the tools that I'm talking about here. Question?
So in your previous slides, you mentioned about how like searching between like given a vertex, find this associated vertices, or given an edge, find the edge nodes in like constant time. Can you like dive a little bit more on that?
Oh, sure. So with CSV, so I should say there's several data structures that you would use to store a graph. If you attend undergraduate computer science course, you would learn that you can either use an adjacency matrix, so you have an n by n matrix with n vertices, and you will put a 1 if that edge from I to j exists, or a 0 otherwise. That's n squared space, and for large graphs and sparse graphs, that's a lot of zeros in a massive data space. If I start looking at millions or billions of vertices, there's no way I can have a dense graph. And so for sparse graph representations, the common data structure may be adjacency arrays or adjacency lists, if you will. So you have one dense vector for each vertex, and then for each vertex, you have a linked list of the edges that are adjacent to it. And you're probably familiar with that. And that is space efficient, but if I want to find out, does an edge from vertex 3 to 7 exist, I can go right to vertex 3 because the index is just the vertex number, but to see if there's an edge to 7, I have to walk a linked list. And that's not constant time. That linked list could have 0, 1, 2, or up to n links in it. So that takes a bit of time to search through that list. With this data structure, we were motivated by a different way to store graphs called compressed sparse row. Compressed sparse row uses 3 arrays to store a sparse graph. There's one array that basically tells you for each vertex what's an offset into an edge array where its edges exist. And then by doing some diffs in that array, you can figure out the number of edges adjacent to each vertex. And then the third array is the value on that edge, if you will. So typically there's 3 arrays, but the problem is from a vertex, you can figure out its adjacent edges, but if I have a particular edge, how do I know which vertices? I'm gonna have to do a lot of searching to figure out for this edge, what are the adjacent vertices? Here on this data structure, we have this map and seg, which I don't have time to go into details here, and we have a paper on this, myself, Dr. Zihui Du, and a few others, where you can go back and forth. If I'm at a vertex, I can directly figure out its adjacent edges. If I'm at an edge, I can go the other way, which is why we call it double index. I guess DI isn't on the slide, but we call it double index graph data structure because it's indexed both ways.
What's the title for this paper?
I forget if it's in the slide deck or not, but if you just search for Bader double index data structure, I bet Google will find it. It's probably on my website, and I don't want to leave PowerPoint, but it shouldn't be that hard to find. Yeah. All of the papers I'm talking about are on my website, davidbader.net. Go to publications and just search for any paper that's got Arachne in the title, and you'll find them. And I think it's from 2021. So everything that I'm talking about here, we wrote a paper about that you can see all of the details. And the first thing that we had to do was create a property graph data structure. So now I want to go through in the time that we have just some of the algorithms that we've implemented to give you a feel for what we're doing. And the way we've worked with Arachne is that we have customers, real world customers, they have a problem. And when they have a problem, we implement the algorithms into Arachne, we make it open source, release it to the world. And then as we have other use cases, then we build out other algorithms. So the algorithms that we have built out were all ones where we had customers saying, we need this, we need that, and so on. I'm not a commercial entity, I'm a professor with a bunch of graduate students and even some high school interns working on this. And so we really build things out as are needed, but we have quite a lot of capability in what's there. So just to give you an example, breadth first search is often one of the first problems that someone will want to run on a knowledge graph or property graph that starts with one vertex and maybe wants to find the distance to every other vertex in the graph. One of the fundamental problems, it runs in linear time, and we want to do this in parallel. This is often a notoriously hard problem to parallelize because there's sort of dependencies related to the diameter of the graph. If you have a graph, the diameter is the longest, shortest path in the graph, meaning that you could have some graphs that are long and skinny, and you can't really speed up walking through that graph that we know how to do in practice. In theory, yes, in practice, no. So here, for instance, we're at the source vertex 0, and it wants to discover how far every other vertex is from the that source vertex. And what we maintain is basically frontiers as we sweep through this graph in parallel. So we start a thing, well, from 0, 5, 7, and 2 are both one hop away. So we put them in this next frontier, and then we discover vertices 8 and 3, then 4 and 6, and then 1 and 9. So this label that I have above each vertex is the distance from the source vertex. And I could also save the edges that I used or mark them as to how I got to discover all of those. So this is, sometimes we actually want to compute breadth first search. Sometimes this is just kind of the motif for the type of algorithm that we want to run that's doing a scan through our graph. And the output that we get is this vector of distances. So imagine you had a massive graph in Arcuda, we would store that graph on the back end on our Chapel server, and then it would just be the smaller output, much less size than the graph itself that we'd pull to the front end and return in Python to the user. And so again, we're working through the graph in these frontiers that are moving as we go iteration through our algorithm. So we created a multi-locale parallel breadth first search, so you don't have to. And the algorithm goes through, and as it goes through, it also is has parts of the graph that are allocated on different locales, and that really is what generates communication behind the scenes, depending on how these are mapped to different locales. So I won't go too much into there. Our code that we created, this is the Chapel code. Again, you don't have to program this because we did. You just call Arachne breadth first search, and this is what's happening under the hood. We have aggregators. There may be ways to improve the performance, but we have a pretty good code that's running. And I guess the slides are available. You won't be able to see what's up here anyway, but it's really not that hard to code. If I was trying to do this with other parallel languages, this would be really, really hard. Most but for search codes on high performance computers, often people are spending thousands of lines of code, and this is something much more manageable in Chapel. And not only that, our speed up that we get, we're using a synthetic graph that's very much like a social network, if you will, and we're looking at running it on anywhere from 2 to 64 locales. And if I pick a particular graph size, this is log base 2 of the number of vertices in the graph, and then there's 16 times that edges. So this is about 1 million vertices and about 16 million edges. As we go from 2 locales up to 64 locales, we're getting speed up. And in fact, this table, what it shows over here is that as we have 64 locales, we're getting a fairly good speed up over running on just 2 locales. So as we add more processing units and locales, we're getting better and better performance. So this is fantastic results over here. And this is all running in distributed memory on multiple locales. This is a very, very challenging problem. And again, that code that I had in the last slide here is competing against, this is a benchmark called Graph 500 that I helped create and co-maintain, where companies like IBM and foreign governments with their own supercomputers are trying to compete to run this exact problem. And we have competitive results with just a fraction of the code and complexity. So I won't go through more of the results. So this uses, question?
So just back to where you're talking about the frontiers. Are the frontiers indexed? I think I missed the.
Oh, the frontiers, imagine I'm in a graph. What I do is I go iteration to iteration, and at every iteration I'm making one hop in the graph. The frontier is kind of the expansion of the nodes that I've seen. The next frontier are all the vertices in the graph that are one hop away, but I haven't reached yet. But I know that they're there because I see them in adjacency lists, and they're not ones I've seen before.
The frontiers were say separate machines themselves. Is that
So right now, this frontier is spread across the entire machine, and we have no idea when we look at the next frontier, are those frontier vertices on one locale, equally distributed on all the locales, skewed distributed across all the locales. We have no idea. It depends on the graph layout initially, and it depends on the topology of the graph. So we make no assumptions. In also many cases, the number of hops that you make, the number of iterations that you make through the graph is related to the graph diameter. Most real world graphs, the diameter is usually less than 20, but it takes a couple iterations till you spread out across the machine. Like you may start in a little corner of the graph and see, hundreds of vertices before you start seeing millions. And then in the middle iterations, you're usually doing a lot of work and using up a lot of memory bandwidth. Then the last couple iterations of these types of algorithms, normally your work is petering out. So your work starts small, big, middle iterations, you have a lot of work, and then it closes down.
So what we're saying is that we are not optimized for, say, network hops themselves. There is no else.
No, that's a holy grail type of problem to be able to do that. And we've spent years on that. Many people have looked at that problem, but it's just really, really hard. So what we do instead is that we hope that if we're really looking at solving those problems, we have much better networks with low latency. For instance, we often use InfiniBand, but there's other networks as well, which have a high bisection bandwidth, have a low latency, 10 microseconds or less, and then they achieve that bandwidth with small messages. So many of those networks 20 years ago, you'd have to have a large message to be able to utilize the bandwidth in the network. Now the network providers or network designers are creating network interfaces with the ability to do smaller messages in order to support applications like graph theoretic applications. Other questions? Yeah, if graphs are dense, then things are much easier. because you often have a lot of work. You don't have to worry about load balance. You sometimes can partition it better because once it's dense, you can divide it up in a more natural way. The problem is most knowledge graphs aren't dense. Most knowledge graphs are very sparse, extremely sparse. So you may have, for instance, we have graphs with trillions of vertices, but the fraction of edges, there would be n times n minus 1 over 2, or approximately n squared possible edges. And the number of edges that we see is something that looks more like n log n versus n squared. So, you know, much, much smaller in terms of the number of edges that we see. Any other questions? So just another example, we're using aggregators here. This is like as we look through the frontier. Without aggregators, maybe I have a locale and it's trying to do some put operations to another locale, and it does them one by one. Each one of these is blocking. So it puts one into memory of that second locale, then it puts this 5, then this 3. I really have to click through all of this, I guess. I mean, this is slow. I'm just gonna sit here clicking as I do it one by one. So this is without an aggregator. They operate sequentially. That was a lot of clicks. With aggregators, for instance, I can aggregate these puts, and then, you know, the number of clicks is the amount of latency or communications I need. This first one happens. These were all aggregated together. Maybe I need a second aggregated put. So now it's just 2 puts instead of, I don't know, 8 or more that I had before, maybe 10. So that's the power of aggregators, to be able to do this in bulk much, much faster. And so we have aggregators at these breadth first search frontiers. So instead of using the edges to do single messages, we're aggregating in these locales all of the communication that goes over edges between different locales as we're sweeping through this breadth first search. And that's giving us a huge performance increase, because now it's more like the number of messages is on par with the number of locales, not the trillions of edges that we see in the graph. Question?
Is that optimized for the number of locales, or is optimized for the network that you have? So you're trying to aggregate based on the buffer size of your network package, or?
Gotta click back a lot.
Sorry, no, that's fine.
So the short answer is, we're just doing a distributed aggregator, right? List distributed aggregator. Right there's our aggregator. That's doing all the work.
You don't know the, yeah.
No idea. We could run this on a laptop, we could run it on a supercomputer, on any graph, and we just have one function called doing all of that aggregation. That's, you know, fantastic. This is without aggregators. My PhD student Oliver created this slide. I think I have some recommendations. So that's breadth first search. You know, there's other, I'm not gonna go through all the details of all the algorithms, but I have a bunch of slides. Connected components is often taking a graph and figuring out the maximally connected subgraphs that I have in the graph. And so here's a graph with 1, 2, 3, 4 components in it. Often we want to pull out a component, or sometimes in knowledge graphs, you may have a piece of the graph that's not connected to anything else. And you ask yourselves, like, why do I have a piece of my knowledge graph that doesn't connect to anything else? That's kind of interesting what's there. We often want to be able to find those things, and connectivity type of problems give us answers to that. So this gives us a lot of answers about the structure of a graph. Often we have some knowledge graphs where we want to find the distribution of sizes of the components in the graph, and so on. There's some existing parallel algorithms to do this, and I won't go through a lot of the details, but many of them are just challenged to be able to do the scale, to do it efficiently. This SV is an algorithm from Shilokh Vishkin. There's a fast version of it. There's something called Connected that uses something called Union Find. There's many algorithms out there to do connected components. And to do it in parallel and to do it fast, we came up with a brand new algorithm that works really well, that we have been inspired by contour lines. At a contour line, you have all of the elevation that's at the same height. And we think about this as each connected component, we want every vertex to be at the same level. I don't know if this analogy works so well, but we really were motivated and called this the contour algorithm. And there's some optimizations like a minimum mapping operator. So what we do in this algorithm is we start by trying to point every vertex to its minimum labeled neighbor. And if you keep doing this, eventually what you'll get is every vertex pointing to a label that's the minimum vertex in its component that you use as its component label. So that's the operator that we've implemented. Again, we have papers and papers on these algorithms. I can't do it justice in 2 or 3 minutes, but I can give you the idea of what's happening inside the algorithm here. So we want to run this, and then our proof and our work is to prove that it converges, and that it converges very fast. For instance, in logarithmic time would be good, and we're able to prove that convergence, that if you keep rehooking to your a neighbor that has the smallest label, eventually everyone will point to the smallest label and use that as their component label. So for instance, here's a graph. It's a very simple graph up here. It's just a set of vertices in a line. They all have unique labels, 0, 1, 2, 3, all spread out. Initially, they point to themselves. And so they're looking for their minimum label mapping. So after the first iteration, here 0 would point to, I guess the way it's put here, 5 will point to 0, 14 will point to 5, I have that here, 12 will point to 13. I don't know, maybe I'm not, actually 12 is greater than its 2 neighbors, so it's by itself. 13 points to 8. 10, its smallest neighbor is 8, so 10 points to 8. You can follow it through. So if I keep running this algorithm iteratively, eventually, when I go through the second iteration, the third iteration, the fourth iteration, and so on, eventually I have my answer that all my vertices using this minimum mapping feature will eventually point to 0. And that says they're all in the same component. So we're able to run this on both real graphs, synthetic graphs, many different shapes, sizes of graphs that I show over here. We ran this on a 32 node cluster with a nice interconnection network on it. And there's a lot of results here, but we looked at number of iterations, and our algorithm has a bunch of variants, but the number of iterations is usually typically just a few. Our execution time, again, too many results to go through over here, but we normally run much faster than the prior best algorithms, and we run in a fairly good time, better than all the other results. So we just have a variety of variants. And then these are the 35 different graphs, or 36 different graphs, I should say, in our tests. Some are real, some are synthetic, but we run very well. And we also show speed up. This is speed up compared to the prior fast SV was the fastest algorithm before. And in almost every case here, I guess in every case, we're running much faster. So we have a new and better algorithm for doing connected components. Question?
Yeah, using just your BFS was not faster to compute
You can run BFS to get connected components, but we have a faster method than BFS. Yeah. So I'll leave it at that. Triangle counting that I mentioned. For instance, here's a graph, and this is a pretty easy one to eyeball up and count the number of triangles. I have 1, 2, 3, 4, 5. So the answer that I want to get is 5. A very simple example over here. Normally graphs aren't this simple to look at. Normally they're big hairballs, and you want to run this. This is our algorithm that we're running, and we have a variant and a new version called minimum search triangle counting algorithm. So again, to do massive scale property graphs, we have to figure out efficiencies or ways, heuristics, if you will, for improving prior algorithms, and also ways to parallelize them. And that's what my group tends to do to make it that we can provide Arachne with this huge capability. So here we've found a way, I'll just go to a picture. We may be inspecting the edge UV and trying to see how many triangles are incident to that edge UV. What that means is we have to go to U and V and see, is there another vertex adjacent to U or V that has edges to both U and V? That would be a triangle. And our optimization is that we go towards the vertex with the smaller number of neighbors first, so that we have to do less of these comparisons. And we can prove that this algorithm has fewer operations, if you will. They're intersection type operations, but we're doing fewer operations by always directing the search by looking at who's got fewer friends in that graph. And we have results that show that this runs very, very well. So we have triangle counting. We use that for truss analytics. How many of you have heard of a truss before? So, wow, this is great. So trusses were have been used in some communities extensively because they're easy to compute, but a lot of tools, I guess, don't have trusses yet. And basically, there are many variants of trusses. I may look for a max truss, a K truss. A K truss is where a user tells me they want a 3 truss, a 4 truss, a 5 truss. Those are probably the most common. I trust that K is that number 3, 4, 5. So if I want a 3 truss, that means every edge in the graph is adjacent to at least one triangle. A 5 truss says that every edge is part of at least K minus 2 or 3 triangles. So there's this K minus 2 factor. I'll just give you an example over here. Here's an original graph, and the edges are colored by their truss, the trusses that they sit in. So if I wanted a 3 truss, in this graph, a 3 truss means that every edge in the graph has to be supported by 3 minus 2 or 1 triangle. And every edge in this graph is part of a triangle. So that original graph is a 3 truss. For a 4 truss, every edge has to touch at least 2 triangles. So as I go through the graph, sure, this edge is in 2 triangles, this one's in at least 2, this one's in at least 2, and so on. But these 2 black edges are not in at least 2 triangles. And so for the 4 truss, I would have the graph minus these 2 edges. That's what I have up there. And then for a 5 truss, every edge has to be in at least 3 triangles. And I get this denser component over here as my 5 truss. And so often an analyst may want to look through these graphs and kind of pick these features where they have a lot of connectivity. And this is a polynomial time algorithm to do it because you compute triangles first, and then for every edge, you see how many triangles it's adjacent to, then you just filter the edges in order to get what truss decomposition you have. And the answer is just this vector that gets returned to the front end. So every edge is part of at least K minus 2 triangles. This is used as a workhorse in some application spaces. And it's used because on these large graphs, traditional community detection algorithms are really, really hard, and it's easy to compute triangles. And this is a really good surrogate for doing some sort of community detection in large graphs. The code, again, I'm not going to go through all the details, but it's pretty simple for us. We're using the co-for-all path-based parallelism in these locales. And this is essentially pseudocode, not different from our actual code for running this in parallel at scale. Often what we'll do is we'll start with the entire graph, and as we ratchet up the K number, we drop off edges till we find the truss that we want, and then we output what we want. Triangle centrality, I mentioned earlier, is a new type of centrality, and there's other centralities that you might have heard of: degree centrality, closeness centrality, between centrality. They all do different things. They all use the word centrality, but they're using some feature of the graph to find vertices of importance or edges of importance. And this is very useful if you're trying to find some influencer in a social network, or you're trying to find some critical point in a supply chain, or you're trying to find some congestion point in other types of graphs, like a transportation type of network. And so they all do well for particular things, but often someone working with graphs will want to run these or others. Here's some more eigenvector centrality. PageRank is a type of centrality, harmonic centrality. They're all finding different importance using different factors to find these features in the graph. But triangle centrality is brand new. We were the first ones to really implement this at scale. And from a theory paper from my colleague Paul Burkhardt, we were able to solve this. In Arachne, our implementation took literally 2 hours and has given us this really incredible way of doing triangle centrality. I won't go through all the details. The paper is from 2021. It's really some new work. And we've been able to pull out some interesting features about graphs that really matter to some customers of ours. Let's see. I'm going to skip through a couple of these. We compared what we were doing. Have many of you heard of graph laws? Sweet spot graph laws, good. Few in the room. This is a really good implementation of some graph algorithms in the language of linear algebra from a good friend and colleague, Tim Davis. We compared our results for running the triangle centrality against sort of the best standard that's out there on a variety of real graphs, and looked at the time for running on graph laws versus some of the variants that we created for running this. And here's some more graphs where we did it. Long story short, the performance, if we look at edges per second, that's what these are showing for the different types of graphs measured on assortivity or fraction of closed triangles, et cetera. Try to tease out where the performance is happening. In all these cases, this is graph laws, which is sort of the current best, and our work or different variants or these other colorful curves. We've been doing much better than graph laws. And I don't have time to go through all the performance results, but we've been able to find some very interesting features and to do this very quickly. And finally, I think the last algorithm that I'll talk about is subgraph isomorphism. And we've been building this out for a property graph coming from neuroscientists. And this is also useful in many other domains, but that was just our collaboration that led to us implementing it. What is subgraph isomorphism? Normally, if you have a small graph of vertices and edges, and there could be labels on them, then you have your big graph that you want to find instances of that pattern in. We've been interested in the problem where you're looking for that pattern exactly. There are also variants that are a little bit less rigid, where you're looking for that pattern, but you could have a missing edge in the full graph, or there could be a vertex missing in the real graph, but it's in your pattern. You say it's close enough. Like, I think I found something that looks like that pattern. But what we're doing is the exact version of this, where we're looking for every instance of that exact pattern with properties in that bigger graph. And in fact, we're doing a variant called monomorphism. And what that says is, if in our pattern, maybe I have 3 vertices and they form a V. So these 2 vertices at the top of the V have no edge connecting them. A monomorphism says in the real graph, I don't want to match to a V where they do have that edge. So if there's a missing edge in the vertices in my pattern, like at the top of the V, then in the full graph, that edge has to be missing as well, or it's not a monomorphism, it's just an isomorphism. So this is a little bit more tighter than subgraph isomorphism. This is subgraph monomorphism. So again, we're looking for both the existence of edges that match our pattern, and also the missing edges in our pattern must also be missing in the main graph. A lot of words that say just what I said. Here's some examples of isomorphic graphs. So this graph on 1, 2, 3, 4, 5, 6 vertices, and this graph on 6 vertices are displayed here, just laid out differently. The vertices are labeled differently, but the types, which are represented as colors, all match up. And if you were to start pitting them to each other, you'd find that these two graphs are isomorphic to each other. So often I may be looking for features in a graph that may be, a feature may be replicated elsewhere in the graph, and I'm looking for that pattern. And that's what it's doing, is giving me a correspondence of vertices from one graph to vertices of from the pattern to vertices of the second graph. Now, our algorithm to do this in Chapel, normally this would be a lot of work, but this is our algorithm. This is it. I mean, it's very simple to implement and to run this in parallel. This would be a grand challenge to try to do explicitly in parallel computing, but with Chapel, it's pretty easy to do. This is using an algorithm called BF2, the state-of-the-art algorithm for finding subgraph isomorphism in the literature, and we have it parallelized and doing quite well. In fact, our results these are hot off the presses. We're running this in the last week or so. We may be looking for a pattern, and these are just some example patterns that we may be looking for. And what I have plotted here is the running time, and the running time of different systems to do it. So this red dots on the bottom is the running time for Arachne that I'm telling you about today. And I should mention, these running times are given on log scales on take it back. This is execution time on a linear scale, linear scales of running time. The blue dots are network X. So you can see the performance difference between Arachne and network X for this type of problem. And then there's another package .motif, and that's the green dots up here. So the running time for network X and .motif are very, very similar, but Arachne has been able to break through the performance barrier and be able to run this much, much faster. So again, this is really current work. This was completed about a week ago. We have a paper submitted on it, but we've been able to take this, and because we can run it so fast, bolt it to work from neuroscientists to be able to study some real brains. Really excited by that. So if you're interested in this massive scale graph analytics, during the pandemic, I helped complete a book that came out about a year or two ago on massive graph analytics. I'm plugging this book, but I get no royalties from it. I sign them away to charity and to students. But I was very fortunate to be able to collect 21 chapters on all types of massive graph analytic problems, algorithms, applications, frameworks, including chapters from colleagues at Neo4j, from NVIDIA Rapids cuGraph that has actually a lot of our work inside of it, graph laws that I told you about, Arcuda has a chapter in here, and so on. 85 contributors who are folks all around the world who've been working on this large graph problems are all included inside this book. So pick it up and take a look if you're interested. And the research that I showed today, building out Arachne and Arcuda, was supported by my research team that I pictured here, research scientists, number of my current PhD students, very diverse set. And then I have undergraduates, Polina, for instance, some master's students, and then I have, they don't fit on the slide, but I have even more high school students that have been contributing. I mean, it's fantastic to me when I can take a high school student who's really, really bright. They can learn Chapel if they know C++ and implement some of the work that I see here. So we're continuing to build out new features for Arachne as we run into customers or those that have some desires, and Arachne does a bunch of things, but in 3 or 4 years, we can't build everything. We build it as it's needed, and we continue to build it. So again, I encourage you to pick it up, to take a look at it. I will just switch gears on my slides. Okay, and just show you this is the GitHub repository where you can find out a lot more. So hopefully there, if you're like me, you need a big screen. Bears are us / Arcuda NGIT is all the code I talked about. There's also a repository for Chapel. Arcuda is Bears are us. And then Arcuda NGIT is the same as Arachne. Any other questions in the few minutes that we have?
I might have missed it, but like a lot of comparisons could be done, it's like, there's no libraries, but like, have you like done comparisons with like graph databases?
Yeah, so we've developed and designed graph databases. The difference here is that, again, NetworkX, we can only run if we're running on a serial or sequential process. NetworkX can't solve most of our problems because it doesn't have the capability to go to gigabytes and terabytes for many of these problems. So in every case where we can test against NetworkX, where we try to run a much smaller problem to compare, we're often orders of magnitude faster than NetworkX.
Will I be able to run like other query languages on it, like Smart Code?
We don't have that yet. I mean, if you're interested, it's all open source and there's the ability to integrate into it. We have been thinking about ways to query the graph, but right now the front end is really running in Python, and we've thought about putting other engines in front. Also, the system is using Chapel on the back. We've thought about having other systems that could run in parallel to Chapel. There's no special tie. Arcuda, we're doing things in Chapel. We could have just as easily run in other frameworks, other Apache frameworks, other things like that. So that's some future work that it's really expandable. And we've thought, you know, for someone who doesn't want to use Chapel, can we plug in modules? The short answer is yes, that it really coexists with other modules. And with graph databases, again, many of these problems, a database is over-engineered. So a graph database is giving a lot of functionality to keep transactions and make sure you don't lose any information. When I'm running on large knowledge graphs and these large graphs that I'm building from data sets, for instance, there's usually a lot of error in there. And I don't need all of the heavyweight processes of a graph database often because it's outside the fidelity of the problems that I have. So it's typically, you know, again, over-engineered. I don't need all of that horsepower. But really, again, why we've gone to this is we want answers that are fast, that scale to large problem sizes, and there's no enterprise or commercial graph database that can scale to the sizes that we're able to run. I'd love not to build this project. I would love that, but there's no other solution. And I work with real customers who want to solve problems, and there's no other solution in the world that can work on graphs at this scale. I say that pretty confidently.
Some at the beginning, I thought everything was graphs. I was curious too, what is it about edge weights or directions that is like quality of that, or is this more for?
So great question. The question, if I heard it right, was about heterogeneity of the graphs, about edge weights and direction. We can handle all types of graphs. We can handle undirected graphs. We can handle directed graphs. We can handle graphs with properties just on the edges, multiple properties like timestamps, labels. We can handle properties on the vertices or not. So it's very configurable, very flexible.
So do you think methods for like graph robustness or resiliency? It's one of our use cases. Is like you take out a node, so like failures cascade or propagate, plus the node do anything in your pipeline or
so we're actually working on that problem right now as you speak. So we just wrote a proposal to improve graph resiliency, and we're actually just starting on that as of last week. So we finished subgraph isomorphism, and that's actually the next thing we're working on is graph resiliency. So I just, again, took my students, we completed graph subgraph isomorphism. That's exactly what we're looking at. In fact, one thing that we're trying to do is any graph algorithms that you would try to run on a knowledge graph. If the graph is small enough and you have perfect information, the algorithm runs very well. When the graph gets big and noisy, what you start finding is many of the algorithms start to fail because of errors in the graph. For instance, I could have an edge, I just ran out of time. I could have an edge in the graph that is a mistake. It goes from these vertices that are very well connected or to these vertices that are very well connected, but that single edge is a mistake and it throws off a lot of edges. So we want to have a ranking or a score that's like a surprise score, that this edge is really surprising. So someone using our framework could say, let's threshold the graph and take all the really surprising things and let's just assume that they're cleaned up. Whether it's a missing edge that we need to put in the graph or an extraneous edge that we want to take out or a vertex that we think is just wrong. And also all the functionality with persona disambiguation. Say two vertices and we really think they're the same. For instance, a person, there's a David Bader vertex, a David A. Bader vertex, a Dave Bader vertex, and it's really, we can tell by the friendship, edges, by my address, are really all the same person. We want to be able to do that merge and do this type of cleanup before we run algorithms on it to get a much more resilient result from the algorithms that we're running. So we're looking at all of these sorts of things in the bucket, or I should say category of doing graph resilience to be able to look at all of these different factors. Any other questions?
David, can you have a question online?
Well, thank you again. Thanks for your attention. Feel free to kick the tires. Send me email if you have questions, and I'd love to see some more Arachne users. Thank you.